the National Electrical Code 2002, there isn't a specific code number that directly mandates the grounding of electrical metallic tubing or EMT sleeves installed in garages. However, it is essential to consider the broader grounding requirements outlined within the code. Section 250.112, titled General, states that electrical systems must be grounded. This grounding serves to prevent any objectionable potential difference. This potential difference could occur between the grounding system and other conductive objects, between the grounding system and the earth itself, and between interconnected grounding systems. The National Electrical Code 2005 introduced a more explicit requirement concerning the grounding of EMT sleeves, but this was specifically for unfinished basements. Section 358.24b, under the heading Grounding, stipulates that in unfinished basements, sleeves must be connected to the building's grounding system. When interpreting the 2002 National Electrical Code, while there is no explicit directive to ground EMT sleeves in garages, the general requirement for grounding electrical systems leaves room for interpretation. It could be argued that this general requirement implicitly includes such sleeves. However, the subsequent specification in the 2005 National Electrical Code, which singles out unfinished basements for grounding requirements, suggests that perhaps the 2002 code did not originally intend to mandate grounding in all locations, including garages. To ensure the highest level of safety and proper grounding practices, adhering to the guidance provided in the 2005 National Electrical Code is recommended, even when working under the 2002 National Electrical Code. This means grounding EMT sleeves in garages, regardless of whether the 2002 National Electrical Code explicitly demands it. Grounding can be achieved through the use of grounding bushings or other methods approved for this purpose. Effective communication is paramount. It is important to clearly communicate the grounding requirements to all electricians involved in the project, irrespective of the specific edition of the National Electrical Code being followed. This ensures compliance with general grounding principles and provides an added layer of protection against potential electrical hazard. It is important to consider the reasoning behind grounding electrical systems. Grounding serves several critical functions. Firstly, it helps to stabilize voltage to earth during normal operation. Secondly, it limits the voltage rise caused by things like lightning, line surges, or unintentional contact with higher voltage lines. Thirdly, it facilitates the operation of overcurrent protection devices. When a fault occurs, such as a short circuit, the grounding path allows a large current to flow, tripping a circuit breaker or blowing a fuse and quickly disconnecting the faulty circuit. Grounding systems generally consist of a grounding electrode, such as a ground rod or a metal water pipe that is in direct contact with the earth. This electrode is connected to the electrical system's neutral point into equipment grounding conductors. Equipment grounding conductors are the means by which non-current carrying metal parts of electrical equipment are connected to the grounding system. This includes things like metal enclosures, conduit, and junction boxes. In the event of a fault, these conductors provide a low impedance path for fault current to return to the source, again facilitating the operation of overcurrent protection devices. Several methods can be employed to ground EMT sleeves effectively. Firstly, grounding bushings can be used. These are special fittings designed to provide a secure connection between the EMT and the grounding conductor. They typically have a set screw that tightens onto the EMT, ensuring good electrical contact. Secondly, grounding locknuts can be used. These are similar to standard locknuts but include a provision for connecting a grounding conductor, such as a screw terminal. Thirdly, bonding jumpers can be installed. These are short lengths of wire used to connect the EMT sleeve to a nearby grounded metal object, such as a metal junction box or a grounding electrode conductor. When selecting grounding methods and materials, always ensure they are listed and labeled for the intended purpose. This means they have been tested and certified by a recognized testing laboratory such as Underwriters Laboratories or Intertek to meet applicable safety standards. It is also important to follow the manufacturer's instructions for installation and use. Regarding the specific application of EMT sleeves around poured concrete lintels in garages, several factors should be considered. Firstly, the presence of the concrete itself does not inherently provide a grounding path. Concrete is not a good conductor of electricity, especially when dry. Secondly, the plastic bushings that are being installed do not provide a grounding connection. Plastic is an insulator and will prevent electrical current from flowing. Thirdly, the length of the EMT sleeve should be considered. Longer sleeves have a greater surface area and a greater potential for contact with other objects, increasing the risk of an unintentional ground. Even though the 2002 National Electrical Code may not explicitly require grounding in this specific scenario, it is generally good practice to ground the EMT sleeve. This provides an extra measure of safety and helps to ensure that the electrical system is properly grounded. In addition to grounding the EMT sleeve itself, it is also important to ensure that the electrical equipment connected to the EMT is properly grounded. This includes the wiring, devices, and any metal enclosures. All grounding connections should be made in accordance with the National Electrical Code and other applicable standards. It is also important to periodically inspect grounding systems to ensure they are in good condition and functioning properly. This includes checking for loose connections, corrosion, and damage to grounding conductors and electrodes. If any problems are found, they should be corrected immediately. When working with electrical systems, always follow safe work practices. This includes energizing circuits before working on them, using appropriate personal protective equipment, and following lockout/tagout procedures. If you are not qualified to work on electrical systems, hire a licensed electrician. There are several resources available for learning more about grounding electrical systems. The National Electrical Code is the primary source of information on grounding requirements. There are also many textbooks, training courses, and online resources available on the subject. Some additional points to consider include the following. Firstly, the size of the grounding conductor should be appropriate for the size of the circuit it is grounding. The National Electrical Code provides tables that specify the minimum size of grounding conductors. Secondly, grounding conductors should be run in the same raceway or cable as the circuit conductors. This helps to minimize impedance and ensure that fault current can flow quickly back to the source. Thirdly, grounding connections should be made with listed and labeled connectors. This ensures a secure and reliable connection. Fourthly, grounding electrodes should be installed in accordance with the National Electrical Code. This includes requirements for the type of electrode, the depth of installation, and the location of the electrode. Fifthly, grounding systems should be tested periodically to ensure they are functioning properly. This can be done with a ground resistance meter. Remember that electrical codes and standards are constantly evolving, so it is important to stay up to date on the latest requirements. Attend training courses, read industry publications, and consult with qualified professionals to ensure that you are following best practices. Grounding is a critical aspect of electrical safety. By following the requirements of the National Electrical Code and other applicable standards, you can help to protect people and property from electrical hazards. Consider a specific example to further illustrate these principles. Suppose an electrician is installing a new lighting circuit in a garage. The circuit will be wired using EMT conduit, and the electrician plans to run the EMT through a poured concrete lintel. Firstly, the electrician should ensure that the EMT is properly supported and secured. This can be done using conduit clamps or straps. Secondly, the electrician should install plastic bushings on the ends of the EMT where it passes through the concrete lintel. This will protect the wires from abrasion. Thirdly, the electrician should ground the EMT sleeve. This can be done using a grounding bushing or a grounding lock nut. The grounding conductor should be connected to the equipment grounding conductor of the lighting circuit. Fourthly, the electrician should ensure that the lighting fixture itself is properly grounded. This can be done by connecting the fixture's grounding terminal to the equipment grounding conductor. Fifthly, the electrician should test the grounding system to ensure it is functioning properly. This can be done with a ground resistance meter. By following these steps, the electrician can help to ensure that the lighting circuit is properly grounded and safe to use. Another important consideration is the type of soil in which the grounding electrode is installed. Soil resistivity can vary significantly depending on the type of soil, its moisture content, and its temperature. Soils with high resistivity, such as sandy or rocky soils, require larger or more numerous grounding electrodes to achieve adequate grounding. The National Electrical Code provides guidance on selecting appropriate grounding electrodes for different soil conditions. Chemical ground rods can be used in areas with high soil resistivity. These rods contain chemicals that leach into the surrounding soil, reducing its resistivity and improving the effectiveness of the grounding electrode. It is important to follow the manufacturer's instructions when installing chemical ground rods. Another aspect of grounding is surge protection. Surge protective devices, or SPDs, are designed to protect electrical equipment from voltage surges caused by lightning, line surges, or other transient events. SPD diverts surge current to ground, preventing it from damaging sensitive electronic equipment. SPD should be installed at the service entrance of a building and at other locations where sensitive equipment is located. The National Electrical Code provides requirements for the installation of SPD. Ground fault circuit interrupters, or GFCIs, are another important safety device. GFCIs are designed to protect people from electric shock. They work by monitoring the current flowing in a circuit and detecting any imbalance between the hot and neutral conductors. If an imbalance is detected, the GFCI quickly trips the circuit, interrupting the flow of current and preventing electric shock. GFCIs are required in wet locations such as bathrooms, kitchens, and outdoor areas. They are also required in construction sites and other hazardous locations. Proper bonding is also crucial for effective grounding. Bonding is the process of connecting all metal parts of an electrical system together to create a low impedance path for fault current to flow. This includes metal conduit, metal enclosures, and metal equipment. Bonding helps to ensure that all metal parts are at the same potential, reducing the risk of electric shock. Bonding jumpers are used to connect metal parts together. Bonding jumpers should be sized appropriately for the size of the circuit they are bonding. The National Electrical Code provides requirements for bonding. In summary, grounding is a complex and multifaceted topic. It is essential to understand the principles of grounding and to follow the requirements of the National Electrical Code and other applicable standards to ensure electrical safety. Firstly, always consult with a qualified electrician or electrical engineer when designing or installing electrical systems. Secondly, stay up to date on the latest codes and standards. Thirdly, use only listed and labeled equipment. Fourthly, follow the manufacturer's instructions for installation and use. Fifthly, inspect and test grounding systems periodically. Sixthly, practice safe work habits when working with electricity. Grounding and bonding are essential for the safe and reliable operation of electrical systems. Understanding the principles and requirements can help prevent electrical shock, fire, and equipment damage.